Hello! Today, the first thing we're going to look at is an oscilloscope. So just behind me here, you can see an analog oscilloscope. And in the video, I showed you some parts of the oscilloscope, but here you can see the screen. So about the screen, notice that you have a grid system and that each grid, one space between a grid is one division. So when we look at the scale here, you can see we have volts/div. On this, we also have two channels. This is a dual channel scope where we have the controls for one channel here, and we have an input for one channel along with an earth, so we can earth it. And then we have the second channel here where we can also use this for earth. But ultimately, we can also use an earthing inside here. We need this attachment to begin with. This is going to help us connect some wires. Now we're getting some sort of different signals just because we're reading some sort of potential difference. But you can see that if we touch the two probes together, there is zero potential difference. There's zero voltage between them. And so our oscilloscope has flatlined and it's not showing us anything. So what can we see? Well, if you look here, this is also an oscilloscope. This is a much more modern oscilloscope. It's a digital oscilloscope. This particular one is called DS213. And one of the functions of the DS213 is that it can also generate some different types of wave. And I'm going to plug in here to the mini oscilloscope probe into the out part. And then if I go through to the other end, you can see the oscilloscope probe here. Now the oscilloscope probe here has a higher resistance setting to protect your oscilloscope or for certain signals, and a more sensitive setting. Also, normally this is the probe and the very end is the signal that you want to measure. But for us, we also need an earth. So that's why we have this little cable here that we're going to attach. And so because this is earth, we're going to put this connect it to the black one, the black side. Okay. Not okay. Okay, we have it connected. Next, I'm going to turn on this. And now it is generating a square wave of 10 kilohertz. But the oscilloscope here doesn't seem to handle very quick changes in the type of wave. Like I'll show you what I mean. Firstly, I'm just going to reduce it to a 1 kilohertz wave, and you can see that as I'm changing it, we're getting some changes here. Now, this is supposed to be a square wave. A square wave essentially goes across, and then it goes almost directly up, and then it goes across, almost directly down, and across and up and down, and so on. But in this case, the oscilloscope really isn't handling it very well. So I'm going to change it to a different type of wave. Sawtooth. Let's go for a good old sine wave. Firstly, we can adjust the size of the vertical part of the wave that we can see on the screen here. At the moment, it's on this setting 0.1 volts per division. So that means if we go up 1 square or down 1 square, that is equal to 0.1 volts. Now, if I just change it to make each square worth even less, that makes the wave bigger, because now it's worth half of 0.1, so the wave is essentially twice as tall. But it's still very messy, isn't it? And we can barely see one wavelength. So this is where we have to change the time scale across the x-axis. That's what we can do with this dial here. Now, oscilloscopes, you can control each wave's voltage per div, but of course all the waves are displayed on the same screen, so you only have one knob for the time per div. So at the moment it's 0.5 milliseconds per div. And if I make that less, what do you think will happen? Well, because each horizontal division is worth less, that means that to display the same wave, because changing these dials, we're not changing anything to do with the wave, that means we need more divisions. So that's the wrong way. We're going to go the other way. Okay, and now what we're on is 2 milliseconds per division. But it's still unstable, and we can't see it very well. So what we need to do now is think about the trigger mode. So down here we've got trigger mode, and we've also got trigger level. And what this does is this tells the oscilloscope where to look for in the wave. And when it finds that point in the wave, it'll try and keep that in the center. So if we just fiddle with this, hopefully we can get a stable wave at some point. Okay, we've caught it. We've caught the wave. So, moving, no, don't. Okay, we've got it again. We've got it again. We can see that if we start the wave here, it seems to go down and up and down and then back up to here, which is approximately 1, 2, 3, 4, 5, 6 divisions. So on the oscilloscope, we've got 2 milliseconds per division. And that means we have 2 milliseconds per division, and we have 6 divisions. So that means the time period for this wave is 12 milliseconds, which would also be equal to 12 multiplied by 10 to the minus 3 seconds. That means that the frequency of the wave is 1 divided by the time period, which would be 1 divided by 12 times 10 to the minus 3, which we're just going to simplify right now. So we're going to say this is roughly equal to 1 over 10 multiplied by 10 to the minus 3. We can move that 10 to the minus 3 on top. So we can say that the frequency is about 1 over 10 multiplied by 10 to the 3. And this would be equal to 0.1, I'm just thinking about how to do it, multiplied by 10 to the minus 3, which if we want to get rid of one of those, it would be equal to about about 100 hertz. So I said 1 kilohertz. If we actually looked on the little oscilloscope, I'm not sure if you can see it on the screen, it does actually say 100 hertz. So what we measured was not exactly 6 divisions, but when we worked it out on the board, we could see that actually we did get about 6 divisions. Now, let's just have a look at some different types of waves.